Welcome friends, Igor is here, and in this video we will discover properties of matrix representations. In this lesson we will discover that linear transformations on any vector spaces can be represented as matrix multiplication as long as we coordinatize the vector spaces. Prove that the operation of addition of linear transformations corresponds to the operation of addition of matrix representations. Prove that the operation of scalar multiplication of linear transformations corresponds to the operation of scalar multiplication of matrix representations. And finally, prove that the operation of composition of linear transformations corresponds to the operation of multiplication of matrix representations. Let's get started. The key result to working with matrix representations of linear transformations is this fundamental theorem of matrix representations. Suppose T is a linear transformation from a vector space U to a vector space V. Let's fix B a basis for U and C a basis for V. This allows us to construct a matrix representation of the linear transformation T relative to the bases B and C. Then, given any vector U in the domain U, we can apply the linear transformation T to this vector and then coordinatize this vector in the vector space V relative to the basis C. Or we can first coordinatize this vector as a vector of U relative to the basis B. This will become a column vector, and then we can multiply this column vector by the matrix representation. The result of these two different approaches would be the same. The vector representation rho C is an invertible linear transformation, so we can also apply the inverse of rho C to both sides of the first equation to obtain the second equation. It says that to compute the value of the linear transformation T on this vector U, we could coordinatize this vector in the vector space U, then multiply by the matrix representation, and finally uncoordinatize this column vector back into the vector space V. The result is the same as applying linear transformation T to the vector U. In essence, what this theorem is saying is the following. If we coordinatize the vector spaces U and V and represent the vectors in these vector spaces as column vectors, then the linear transformation T becomes multiplication by the matrix. Here is a commutative diagram illustration of the first equality. If we start with a vector in the vector space U, then there are two ways to get to a vector in Cm. First, we can apply the linear transformation T and then coordinatize this vector relative to the basis C. Or first, we can coordinatize the vector and then multiply this vector by the matrix representation. The result is the same. Inverting the arrow that corresponds to rho C yields the second equation. To get from the vector space U to the vector space V via the linear transformation T is the same as coordinatize the vector, multiply by the matrix, and then uncoordinatize the result. Let's prove this result. Let's say that the basis B consists of vectors U1, U2 through Un. We take any vector U in the vector space U, and it can be decomposed uniquely as a linear combination of the vectors in the basis. Let's compute this expression. First, we recall the definition of the matrix representation of the linear transformation. Its columns are defined as follows. You apply linear transformation T to each of the vectors in the basis B, and then you coordinatize these results relative to the basis C. Also, what is rho B of U? The vector representation takes the presentation of U as a linear combination of the bases, and it picks up the scalars in this linear combination and puts these scalars into the column vector. Now we're dealing with matrix vector product, and it is equal to the linear combination of the columns of the vectors, where the scalars come as components of the vector. But rho C is a linear transformation, therefore it respects linear combinations. also T is a linear transformation, and therefore it respects linear combinations. But now it remains to observe that the vector in parentheses is simply vector u. This equality is exactly what we were trying to prove. Here's an example that illustrates this result in action. In the last video, we considered this linear transformation from the vector space of polynomials to the vector space of matrices, and we computed the matrix representation of this linear transformation relative to two nice bases. Basis B of the vector space of polynomials and the basis C of the vector space of matrices. Let's take one random input of the linear transformation. It's a polynomial of degree at most 3, and let's compute the value of the linear transformation in two ways. First, we compute the value of t directly. We have a formula for t, so we can write the matrix value, simplify it, and this is the value of the linear transformation on this polynomial. But now, let's do the same computation using matrix multiplication. The problem is that we cannot multiply this polynomial directly by a matrix, but first we can coordinatize this polynomial, make it into a column vector, and then multiply this column vector by a matrix. The advantage of choosing a nice basis B is that it is easy to coordinatize polynomials relative to this basis, and we also know the matrix representation. So if we perform this matrix vector multiplication, the result is another column vector, and then we uncoordinatize this vector in the codomain, which is the vector space of 2 by 2 matrices. Uncoordinatizing vector is easy. We just use the components of the column vector as scalars in the linear combination of the vectors from the basis C. We compute this linear combination, and as you see, we get the same result as in the first computation. To establish further properties of matrix multiplications, we need one technical result. Suppose we have two matrices of the same size, A and B, and suppose that AX equals BX for all possible column vectors X, then A is the same matrix as B. Let's label the columns of matrices A and B in a natural way. We assume that AX is equal to BX for all possible vectors X. So in particular, this equality holds for some convenient specific choice of the column vectors. In particular, these equalities hold if we substitute for X all possible standard unit vectors. But you can easily check that if you multiply a matrix by the jth standard unit vector, the result is the jth column of the matrix. We assumed that A times EJ is the same as B times EJ. It means the jth column of the matrix A is the same as the jth column for the matrix B. But this holds for all columns, therefore A and B are the same matrix. And now we are ready to prove that the matrix representation of the sum of the linear transformations is the sum of their matrix representations. In other words, the operation of addition of linear transformations corresponds to the operation of addition of matrices. Let's assume that the dimension of the domain U is equal to n, and we are going to take an arbitrary vector x in Cn. Then we uncoordinatize this vector relative to the basis B, and we will get a vector u in the vector space U. Let's see what happens when we multiply the vector x by the matrix representation of the linear transformation T plus S. The vector u is the result of uncoordinatizing the vector x relative to the basis B, therefore the vector x is the result of coordinatizing the vector u relative to the basis B. And now we use the fundamental theorem of matrix representation. Next, let's recall the definition of the addition of linear transformations. The value of T plus S on the vector u is T of u plus S of u. Rho C is a linear transformation, therefore it respects vector addition. But now we are going to apply the fundamental theorem of matrix representation to these two expressions. But now we are going to apply the fundamental theorem of matrix representation again, but now separately to the transformation T and transformation S. Matrix multiplication distributes over addition, therefore we can simplify this expression as follows. The last step is to recall that rho B of U is the vector x. But now this shows that the matrix representation of T plus S and the sum of the matrix representations of T and S multiply all possible column vectors x to the same result. By what we just proved, these matrices are the same. Next, let's prove a similar result for scalar multiplication. The matrix representation of a scalar multiple of a linear transformation T by the scalar alpha is the same as the scalar multiple of the matrix representation of the linear transformation T by the scalar alpha. In other words, the operation of scalar multiplication of linear transformations corresponds to the operation of scalar multiplication of matrices. Same setup as in the previous proof, so I'm not going to go over this. And we're going to look at the product of the matrix representation of alpha T and vector x. We recall that x is equal to rho B of U, and then we apply the fundamental theorem of matrix representation to the linear transformation alpha T. By the definition of scalar multiple of a linear transformation, the value of the linear transformation alpha T on the vector U is the value of T on U multiplied by the scalar alpha. Rho C is a linear transformation, so it respects scalar multiplication. And now we're using the fundamental theorem of matrix representation for the linear transformation T. We are free to move the scalar multiple anywhere in the matrix product, therefore we can rewrite this expression as follows. And then it remains to recall that rho B of U is equal to the vector x. Once again, these two matrices multiply all possible column vectors x to the same result, therefore they must be equal. Finally, a remarkable result that the composition of linear transformations corresponds to multiplication of their matrix representations. Suppose we have a linear transformation T that goes from a vector space U to a vector space V and another linear transformation S that goes from the vector space V to the vector space W. In this case, the codomain of T is the same as domain of S, so we can compose these linear transformations. We also fix bases B of U, C of V, and D of W. Then we can construct the matrix representation of the composition of S and T, which is a linear transformation that goes from U to W. So this matrix representation is taking relative to the bases B and D. B is a basis of domain U, and D is a basis of codomain W. This matrix is equal to the product of the matrix representations of T and S separately. I will help you digest the proof of this result by using this visual aid. The diagram on the left corresponds to the individual transformations S and T. Notice how we coordinatize each vector space relative to its own basis, and how we get two matrix representations, one representation for T, one representation for S. The diagram on the right corresponds to the composition of linear transformations. And we're saying that the product of two matrices on the bottom of the left diagram is the same as the matrix on the bottom of the right diagram. We are still going to use this visual aid to go through the formulas in the proof. We start with the same setup as in the proof of the previous two theorems. Let's look at the product of the matrix representation of the composition of linear transformations with the vector x. First, the vector x is rho B of vector U, and we are going to use the fundamental theorem of matrix representation applied to the composition of linear transformations. So pay attention to the diagram on the right. This is the fundamental theorem that corresponds to this diagram. Notice how this computation involves coordinatizing vector spaces U and W relative to row B and row D respectively. Next, we use the definition of the composition of linear transformations. And now we are going to use the fundamental theorem of matrix representation for the linear transformation S. We treat the vector T of U as an input of the linear transformation S. This is some vector in the vector space V. And to see what I have done here, pay attention to the diagram on the left, the right square of this diagram. Next step is to apply the fundamental theorem of matrix representation to the linear transformation T. To see how it was done, pay attention to diagram on the left, but now the left square of this diagram. Next step is the associative property of matrix multiplication. And the last step is to recall that row B of U is the vector X. Once again, we see that these two matrices multiply all possible vectors X to the same result. Therefore, they are the same matrix. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will prove that the kernel of a linear transformation is isomorphic to the null space of its matrix representation. I will see you later.